So today we're going to look at circuits like this, LCR circuits. First step, write down what the total impedance ZS is in terms of S. So using your Laplace transforms, write down the expression for the total impedance, resistance, and then try and combine that into one fraction. So, resistor is just 1, 100 Henry inductor is 100S, and a 0.1 farad capacitor is 1 over 0.1S. So that's our three terms. Now we want to combine them into one fraction, so we look at the denominators. The denominator is 0.1S for this, so we could do with the denominator being 0.1S for that and 0.1S for that. So make the denominator 0.1S for all three terms, and then you can add them. So the first term is going to be 0.1S over 0.1S. That's just 1. If I multiply the top and bottom of the second term by 0.1S, I get 0.1S times 100S over 0.1S, and the last one is already over 0.1S. So I get that. So now I can write 0.1S plus, tidying the second one up a bit, 0.1 times 100 is 10 S squared, plus 1 all over 0.1S. So that's our term for ZS as one fraction. Just make sure you see that, because it's the same every time. If I want to combine components, I want it to write it as one fraction, so that I can then put it into Ohm's law to find the current, which is what we're going to do. I want to now use Ohm's law. So as we did last week, if we look at this, then the voltage is just 10 over S, because it's a step voltage. So now the current is the voltage over the resistance, so that's going to equal 10 over S over this 0.1 S plus 10S squared plus 1 over 0.1 S. What we do now is, you're right, what we do now is we look at this bottom fraction, and we've got one fraction, 10 over S, that we're dividing by another fraction. So what we do is invert the bottom fraction and multiply. That's the trick. So, and it's always the same. What I do at this step is I now say that is 10 over S multiplied by the inverse of the bottom fraction, which is 0.1S over 0.1S plus 10S squared plus 1. So check that step. Make sure you see it, because it's what we do every time. Invert this bottom fraction and multiply. Sorry? Now we can cancel out these S's, top and bottom, because this is think about this is all times by that, so that actually that expression should be in a bracket. So we can cancel out these S's, top and bottom, and 10 times 0.1 is 1. So we end up with this equaling 1 over 0.1S plus 10S squared plus 1 for the current. If we think about our Laplace transforms from last time, what we don't like is S having any term in front of it, so I could do with getting rid of that 0.1. So times everything by 10. Sorry, it should be S squared, shouldn't it? Yes, thank you, 10S squared. Yeah, so actually scrub that last bit. Yeah. Now we would start thinking about looking at our Laplace transforms, trying to get S on its own, but we're struggling because if we look at our Laplace transforms now, we actually, the only one that looks anything like what we want is this one. This is what we're after, this one here. And what we want to do is try and write this bottom term like that. And then we can suss out what omega is and what A is, and then we can say what omega and A is in here. What we're going to end up with is some sort of damped sine wave. So if I were to switch this circuit on, it would be some sort of oscillating charge in the circuit dying away to nothing. And that's what this is implying here. So our problem now is to get this to look like that. And that involves the method of perfect squares. So we're going to have a look at that and then come back and apply that method to this problem.